Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my great pleasure to introduce Cesare. I think it doesn't need introduction to those who are looking into formal logics. So Cesare is one of the staples of automated deduction SMT communities. So now to Cesare.
Thank you for the introduction and the invitation. So I'd like to tell you today about a new solver that we have developed to reason about strings and regular expression, character strings and regular expressions in the context of satisfiability modulo theories. So this is joint work with a few people at Iowa, postdocs and students of mine, and our collaborators at NYU, Morgan Dieters, who sadly passed away a few months ago, and Clark Barrett, who's the co-leader of the CBC4 project that we do jointly with Iowa and NYU. So our motivation to be able to reason about strings is, well, mostly security applications, where strings are often involved in operations that, well, expose security vulnerabilities. For instance, this code here is a vulnerability. Can you see which one it is?
Concurrent program. Is there interference from other threads?
Unfortunately, the vulnerability is a lot simpler. Well, fortunately for us, unfortunately for users. And, well, so what's the idea here? That you have to enter a password, which here which is hard-coded. I'm calling that password. And then if what you enter is the sequence of letters in the password string, then you have access to some protected part of the system. But the way that's declared is by, let's see, can I use a point? Do I have a pointer here? Yes. Is by using a buffer, and then right after that, a character pass. So if I force a buffer overflow here, I could rewrite pass with Y and then get in. Okay.
Initializing pass at all.
Well, people do that. That's
it might be randomly initialized to Y.
Yes, this is a bad program. We kind of made it up to make the case here. But you'd be surprised, the sort of vulnerabilities that you discover. Well, you probably know this, that you can discover. So, I'm sorry?
Vulnerabilities here are uninitialized variable and buffer overrun, neither of which is to do with regular expressions. Is that right?
Well, there is regular expressions involved here, right? Because you need to check that what you enter is letters, this sort of stuff.
So is there a problem with that too? Is that a vulnerability in this program as well?
That we're using regular expressions, or not in this particular case, but in terms of formalizing this so that we can discover the vulnerability automatically, we do need to reason about strings and regular expression membership in regular languages. Well, you probably know about satisfiability modulo theories. SMT solvers have been shown to be pretty good at reasoning about specific domains. One thing we would like to do is convert this problem into a logical problem that we can give to an SMT solver specialized to reason about strings, and see if we can discover the vulnerability, which is essentially, can we get to a point where pass is Y? And, well, in fact, since we have implemented the specialized string solver that I'm going to tell you about already in CBC4, CBC4 can actually discover this vulnerability and give you, in fact, a potential exploit. That is, by solving these logical problems and finding it satisfiable, it's able to give you a security exploit. Yes?
So where did the buffer overrun show up on the right?
And the fact that we have a...
like the adjacency of buffer and pass are somehow encoded on the right.
Yes, so here we have built where is the pointer? An input string here that overflows. So there's a y at the end.
So somehow in the text on in the right-hand column,
yes,
you've encoded the fact that buff and pass are physically adjacent.
Yes.
I don't see where you've encoded that.
Yeah. Well, I mean, I'm skipping the steps here, but this would be, you know, a traditional standard encoding, for instance, that you have in Boogie or Daphne, you know, to talk about local systems, where you go from the code and knowing the semantics of the programming language, you convert that into a logical problem that corresponds to the operational semantics.
This particular one, where is it encoded in the right that buff and pass are physically adjacent? I'm just not familiar enough with the language in the right-hand column.
Here,
Ah.
in the fact that
input.
the input is a concatenation of these two. Again, don't take this literally. I mean, this is not the actual translation that you will get, okay? So I had to manipulate this to make it a little more readable, but that's the idea, that you get here the fact that, I mean, you translate it in such a way that you capture the fact that these are adjacent, but let's not focus on this, which is about how you properly translate a problem into a logical, how you translate a security or safety problem into a logical formula, which is not the focus of the talk. There are ways to do this. What I'd like to tell you about is how we can solve these problems here, because until recently we were not able to do it. That is, we were not able to reason about strings in an efficient way. Well, mostly because people hadn't gotten to thinking about this problem seriously, at least in the SMT community, although in other communities people had attempted. And also because the problem is actually fairly hard. So if you consider just word equations, which are just equalities between string expressions that contain characters and concatenation and variables, and that's it, the problem is decidable. This was discovered after a long time. It was a surprisingly hard problem to prove. But the best algorithms that we have right now are piece-based. We don't actually know the complexity of this problem, but the best algorithms are actually quite inefficient. If you throw in length constraints, that is, you also add to that, in fact, linear arithmetic constraints that involve length of the string, we don't even know whether the problem is decidable or not. And if you throw in additional string functions like replacement and substring and so on, the problem is actually known to be undecidable. On top of that, I said we're also interested in membership constraints because they show up in problems like the ones that I described earlier. So if you put them all together, we don't actually know whether they are interesting fragments of this set that we can reason about efficiently. Okay? But our focus has been that. You know, we know this problem is hard. Can we write efficient solvers that perhaps are not complete, but definitely we would like them to be sound and, well, good most of the time, that is able to give us an answer in the sort of cases we're interested in. Now, in fact, there is some work now being done in trying to identify decidable fragments of this large language, and I'll mention a few things later about that. So again, what was our objective? We want to build a string solver that is able to reason efficiently about strings of unbounded size. This is important to stress, because if you bound the size of the strings, the problem becomes trivially decidable. And in fact, there are existing solvers that do this. That is, they require you to give an upper bound, and then they convert the problem into a bit vector problem. Okay? We do not want to do this. We would like to reason about arbitrarily long strings, and although we do want to have length constraints, okay, and perhaps include string manipulating functions, like as I mentioned, and do regular membership. In fact, it turns out it's useful or necessary to talk about symbolic regular expressions, which are regular expressions where you allow variables of type string. And these expressions, in fact, denote non-regular languages, making the problem harder. So to be a bit more concrete, oops, it's not time to take a break. to be a bit more concrete, we want a language that allows us to write what I'm going to call atomic terms, which are string constants, again, of arbitrary length and variables, and then concatenation and length, a length operator. A language like this is going to be our core language, and then on top of that, we want to add additional stuff. I will discuss the core language here simply because this is already hard enough to talk about. But we have also worked on how to deal with regular expressions and, as I said, additional function. I'll mention this briefly. I'll focus on the core language now. And also because as far as basic string manipulation functions are concerned, you can find a way to reason about them by reduction to the core language. So string to int to string, prefix, suffix, they can convert it to word equations. Similarly, the index of and so on, perhaps using intermediate translations, and having word equations and constraints over bounded integers. In these conversions, quantifiers are involved, so the reasoning about them becomes more complex. The underlying principles here in trying to come up with a solver that deals with this language for us is that of using algebraic techniques. Why we want to implement this into an SMT solver. If you know how SMT solvers work, although technically you could use any decision procedure that is appropriate for the domain, at least in model solvers, it's important that certain properties, that the procedures have certain properties, such as incrementality, ability to backtrack, and things like that are easier to satisfy if you can write your specialized solvers to essentially use algebraic manipulation rules. So deduction and algebra is the approach that we want to follow, but again, specialized to this domain. Now, this contrasts with other approaches that you found in the past to reason about strings and regular expressions that, for instance, will reduce the problem to an automata problem and then use automata techniques to do this. This is not appropriate in SMT solving because of the need to backtrack and assert things very quickly and assert things incrementally. It's not easy, at least we don't know yet, how to do this with automata that need to be constructed and then perhaps thrown away right after. Right? That's not efficient. So we came up with a solver for this language that we could understand as having this general architecture. So first of all, we work in the context of SMT solvers following the DPLL architecture. How many people know about this? Okay, so the majority of you, but just very quickly for the others that do not know this. The DPLL architecture is essentially a general architecture for modern SMT solvers where you have Boolean reasoning delegated to an efficient set engine and then reasoning about simple forms of constraints in a specific domain done by specialized solvers. And the simple form of constraints is atomic formulas or negated atomic formulas. The specialized solvers and the set engines work together to solve quantify-free problems over the language in question. You can throw in reasoning about quantifiers using additional modules. Let's ignore that for now. So let's consider just quantify-free constraints. The DPLL engine, the DPLL architecture as a so-called DPLL-X engine, the SAS solver, and then a bunch of auxiliary engines. So here we'll be using a standard one for linear arithmetic constraints, this LIA solver that I write there. Essentially a standard one for constraints over uninterpreted function symbols, the EUF solver there. And then this new solver that we have developed to reason about strings. So what is the idea essentially? Well, first of all, if you have problems that involve strings and linear arithmetic constraints over length, for instance, there are standard ways to separate the problems into the two domains and then solve the original problem by a collaboration between a string solver and an arithmetic solver. So this is pretty standard. I won't say much about it. The other trick that we're using here to build a specialized solver for strings is that of building that on top of an EUF solver. So EUF solvers reason about equalities and congruence in general. and compute congruence closures of a set of equalities. On top of this, we will add additional specialized rules, additional deduction rules specialized on strings. Okay? So we'll do the easy stuff using the congruence solver. Then on top of that, we will add additional rules. And the additional rules are the ones that are incorporated into the big picture that you have, the big square you have on the right, the string solver. The string solver itself essentially takes constraints and produces new constraints using a deductive approach, but it does that in a particular strategy. And the strategy here is illustrated by the various boxes at a very high level. In fact, the strategy is more complex here. I do need to simplify. And the idea is that you do a series of steps in sequence, and each of these steps can produce new constraints, new equations on inequations over strings. I'll focus on equations and inequations here. And these constraints are fed back into the general engine that also perhaps distributes some of these constraints to the other solver, in particular constraints that involve length in this case. So at any stage, if any of these steps produces something, is returned back to the engine, and the process starts again. You go from one step to the next if there is nothing to give to the engine. And so the workflow here is you start where the engine has a set of constraints, which are going to be, again, atomic constraints over strings or negated atomic constraints. We'll call that set M. That is given to the string solver. A bunch of steps are taken that might produce more stuff. They are given back to the engine. This process continues to completion, where completion here is you discover an inconsistency. And the way we discover inconsistency is by discovering trivial inconsistency. Or you saturate. That is, no more rules apply. So we show that when the process saturates, you've actually found a model of the original quantify-free constraint. Okay? Again, we allow arbitrary quantify-free constraints, but the Boolean stuff is managed in a standard way by the SMT solver, the rest of the SMT solver. So let's ignore that. Let's consider just equalities and inequalities between strings, as well as atomic constraints over arithmetic. Yes?
The information is propagated back to the DPLL engine. I mean, that's decisions or consequences or...
These are just consequences, as I'll show. And they are typically atomic, well, they are literals. Okay? So you pass literal, there are entails. Or if you have a situation where you don't actually have nothing that is entailed, but you have possibilities, you pass a possibility, which is a decision. You say, well, assume this. Then the solver will continue. This theory here is not convex in the technical sense that we have in SMT. So often you need to make guesses, even within the string solver. These guesses are passed to the Boolean engine in the standard way. All right, so let's consider this problem here. We have these two word equations, and then this length constraints over x and y that are strings. They're variables, and a and b are characters. Okay. This problem satisfiable. Dot means concatenation. So we want to find two strings where x is longer than y that satisfy one of these two constraints. Right?
Y is empty, x is A.
Sorry? Yeah, it is satisfiable, right? So there's a bunch of ways to satisfy. So we would like to discover that. So the first thing you do, as I said, is to split the problem into an arithmetic part and a string part, which in this case is trivial. We also make guesses when we have disjunctions about which parts of the disjunction we want to work on. And so the subproblem we're actually focusing on right now is the conjunction of these two red things. One goes to the arithmetic, the other one goes to the string solver. Okay? Notice, as usual, that the two sets of constraints share variables, and so they're not disjoint. Collaboration between these two solvers is going to be needed. In this case, you don't have a choice for the first one because it's asserted it's an atomic constraint. But you have a choice between these two because of the disjunction. Right? To satisfy these two constraints, you must satisfy the first and then it's enough to satisfy one of the disjuncts of the second.
So are these constraints by hypothesis all in whatever it is, CNF?
Yeah, they're typically, internally they are in CNS. The input to the solver is arbitrary, but there is a
So you
CNF.
put them in CNF, and then you're saying you pick one for each of the conjunctions. Is that right?
One for each of the disjunctions.
Sorry, because, yeah, that's right.
One disjunct per
Right.
clause.
So there's an exponential number of combinations you can
Yes, but of course this is not done eagerly. It's done as needed and using the SAT solver and so on. So again, this is where the power SMT solvers comes from, or some of the major factors in the power SMT solvers that can reason about the disjunctive structure of a problem very efficiently by having search heuristics, by learning about wrong choices and so on. This is, again, standard SMT stuff that I won't discuss.
So that's part of
but-
that engine bit.
Sorry?
It's part of that DPLL bit.
Exactly.
Okay.
And the interaction with the other ones. Because, for instance, when the DPLL engine has to guess, it does ask the solvers if they know something about the guess that it's about to make, because otherwise, it's unnecessary.
Okay.
Also, wrong guesses lead to unsatisfiability, and then to learning why you made the wrong guess, and then trying to avoid it later, and so on. Okay, so at this point, the first check is, do we have a conflict in our set M of constraints? And the only conflicts we check for are, do we have a disequality between two identical terms? Okay? That is, we want to reduce the discovery of a conflict to this simple problem. We don't have it right now, so we continue. Yes?
Can I go to the previous slide? Can you go to the previous slide?
Yes.
So in the input, you had X concatenated B, and in theory strings, you have X concatenated with Z. Is it just a typo?
Oh, yeah, that's a typo. I'm sorry. Yes.
So which one should we do?
B. Or anything you want. I mean, this is just a pretext to tell you about the mechanism, right?
Right, but there isn't
I mean, it's
a magic
okay to
change.
debug. It's better to have slides with no typos in it, but you can reason modulo typos at this stage. I mean, in this venue, I assume. Okay, so I do have Z here, so let's see how that works out. So let's say it's Z.
A variable, not a character.
Z is a variable in this case. So A and B are the characters. Okay? It doesn't change the nature of the problem here. Okay, so there are no disequalities. We move to the next step. So what we do in that step is to propagate from the string solver any constraints that involve length that are of interest to the arithmetic solver. And the only constraints that we propagate are of the form length of a variable equals length of another variable or not. Okay? So in this case, either that one, or when we start, constraints of this form, that we say that the length of the left-hand side is equal to the length of the right-hand side, but then in fact, by using standard algebraic rules about length, we put it into a form where the length is applied only to variables. Okay? So effectively, length of x will be considered by the arithmetic solver as an integer variable. Okay? The arithmetic solver will just see something that is called length of x and treat it as a variable. So we have this constraint. We deduce this length constraint. We pass it to the DPLL engine so that it can communicate it to the arithmetic solver. Notice that this is the constraint propagation step that I was mentioning, but there is an opposite propagation step that is it goes in the other direction. So for instance, in this case, by having this arithmetic constraint, the theory solver can give the series string this constraint here. It's saying that the length of x and y are different, which is a constraint that the string solver understands. Okay? The string solver does not understand arithmetic, but does understand equality and disequalities between length applied to a variable. So this is the sort of exchange of information between the arithmetic solver and the string solver that is needed, and in fact enough to make sure that the two solvers cooperate in a complete way, so to speak. The next step, when we're done with propagation, and notice again, I should stress, every time we propagate something, the whole process restarts. Okay? We propagate inequality, we give it back, then we check again. Do we get something into M, new stuff? Do we have a conflict now? Then do new propagations and so on. The next step is to say, well, we do have variables, string variables. Do we have string variables? And if we do, let's guess what the length of these variables is. But we guess it at only the basic level. We guess whether the variable must be given the empty string as a value, or can be given a non-empty string. So this is the only guess. The guess is done one at a time, but eventually a sequence of guesses might lead to one of these situations. Not necessarily all of them. Some of them might be immediately discovered to be unsatisfiable, and so we'll recover. But essentially, we will consider these 4 cases, at least in principle. When that is done, that is, when you figure out for all variables where you want them to be empty or not empty, then you try to normalize equations between variables. So what is the idea? Sorry, equations between terms. For every string term in our problem, we want to produce a normal form, where a normal form for us will be a concatenation of atomic terms, where an atomic term, remember, is either a variable or a string constant. So this is our normal form, just a sequence of concatenations, modulo associativity of atomic terms. And to be able to do this, then we process the various equations in a way that allows us to get the normal form, as I will show in a couple of examples. Okay? This is, in a sense, one of our contribution. That is, to be able to normalize using strictly algebraic techniques. Once that every term has a normal form, and we haven't failed yet, what do we have? We have a set of equivalence classes that we have been able to deduce. And for each of these equivalence classes, we have this normal form available. That is, we know that the terms in there are equivalent to this normal form. At that point, we have to worry about cardinality. We have to worry, because remember, we have length constraints. Do we have enough string constants to assign to these equivalence classes? What we do then, we partition the equivalence classes into buckets, where 2 equivalence classes that are not supposed to be merged go into the same bucket if we want them to have a value of a given length, same length for the 2 equivalence classes. Different values, same length. They go into different buckets if we want the equivalence classes to have values of different length. Okay? This partitioning process is partly driven by what we know already and partly driven by guesses. Okay? So again, there's guessing steps here that might restart the whole thing every time. Once we're done with that, and well, let's see if I actually have this. Well, once we're done with that, we'll go to check satisfiability, but I'll describe this later. So how do we do partitioning? So again, let's look at our example here, where we have this set of equalities. So these are the string equalities, and these are the length constraints that we have. Given this problem, we notice that, well, since these 2 strings have to be the same, and x and y have to have the same length, right, we can slice them off from the problem. X and y have to be the same length, so the rest of the string, that is z in this case, and yab also have to be the same length. And then we need to figure out, what z is. Okay. So in this case, we also know that z has to be different from w. So the slicing in particular is simple. Okay. So again, x and y have to be sliced off because they have the same length, or can be sliced off. And then we know by these constraints that z has to have the form w, it has to start with w, and then continue with something else that we call z prime. So we literally add that information as a constraint, where z prime is a fresh variable. Okay? And notice that now the slicing process will continue, to completion eventually. And when you're done slicing, then you have added new constraints that tell you what variables or what terms have to be equal to what terms. given
leave
what
the
you
old
know.
constraints there.
Yes, sorry?
You leave the old constraints there.
Yes. This is, well, monotonic reasoning because we're doing this by deduction, so we never throw away constraints.
Okay.
The only case in which throw away constraints is when we backtrack, right? But in terms of a calculus, in fact, we do describe this in terms of a calculus in our paper. You can understand this as a tableau calculus where every choice gives you a different branch. So within the branch, we'd never throw away anything. Of course, we might deactivate in practice some stuff. That is, some constraints have given us everything that they have to give us, so we will ignore them, which you could understand as removing them. But in effect, you remove stuff only if you replace it by equivalent set of constraints. Often, however, the deductions are deductive, but not in an equivalent preserving way, so we need to maintain the old ones. Okay, so this slicing process here can be done in an analogous way also with disequalities. Let me skip that. I hope you get the gist. The difference being, of course, that with disequalities, when you slice off any prefix that has to be the same, at some point you want to discover that pieces of the two terms on the left and the right hand side of the disequality are in fact different, right? Otherwise, you have an inconsistency. That is, you might end up equating stuff that you shouldn't. Now, notice how the slicing process also sort of narrows down the kind of guesses that you have to make. Right? These two guys here are supposed to be different. But I know that x, well, trivially in this case, x is equals to y. So the difference cannot be in that prefix. It has to be later. Okay? And so you make the guess versus that z and w are different and see how that goes. And again, you might be the wrong guess, then you recover from wrong guesses and try again. There is a challenge in doing this sort of slicing, which has to do with the fact that our variables are unbounded. Okay? If you know bounds on these variables, then this process, the slicing process, is guaranteed to terminate. Because every time you slice, you're getting for sure something smaller. That's not the case with unbounded strings. This is part of the difficulty. In a sense, we could say that this is the point that makes the whole procedure for word equations so complicated. Okay? The ability or the possibility of having cycling situations like the one that you have up there. Okay? So you go basically from a linear problem to a, well, DP space solution. Algebraists think that the problem is actually NP complete, but again, we don't know. So, first of all, is this constraint satisfiable by itself? A, B being characters, and X a variable. Yes? So this is a deceiving problem. It's actually unsatisfying. You could give an inductive argument for it. Try the empty string, definitely doesn't work. And then you can show that a longer string actually won't work either.
So the strings are unbounded but finite.
Unbounded. They were finite. The problem would still be unsatisfiable, but you would discover it in a sense more easily.
An instance of x where x is infinitely long.
Oh, no, sorry. The strings are all finite, but the variables could have unbounded. Well, could be assigned arbitrarily long finite strings. Okay. But let's apply a process, a slicing process here. See what happens. Excuse me. Well, x is to start with b. If you look at that. So we slice the problem by exactly saying that. The x looks like b followed by x prime. But then, if you replace x by this in here, right, replace x by its equal, bx prime, you get bx prime a, b x prime. So you can slice off the b, and you're having this derived problem here with x prime, which is exactly the same form as the original one. So we produce a variant. We have not made any progress. Again, why? Because x prime x and so x prime can have arbitrarily long length. If we kept slicing like this, we will go into a loop. Okay? So in fact, our procedure is not complete because of similar problems. And incompleteness shows up exactly in situations where you have these cycling things for unsatisfiable problems. Okay? That is, it'll try, if you have multiple occurrences of the same variable in one equation, it might end up keeping slicing over and over. Now, this particular case we know how to address. Okay? So we have a rule that actually breaks the cycle here. But there are other cases that we're not addressing. Okay?
And by incomplete, you mean goes into a loop.
Sorry?
By incomplete, you mean it goes into a loop.
Incomplete, by incomplete, I mean refutationally incomplete, that is unable to discover that the input problem is unsatisfiable. Okay? When the problem is satisfiable, we have a strategy that is guaranteed to find a solution. So we actually loop in the unsatisfiable case, which, if you think about it, is a strange thing because this is first-order logic, and by completeness first-order logic, you know that in the unsatisfiable case, you can always find a proof. Okay? But notice we're not using standard first-order logic rules here. We're using a specialized system, which is meant to be efficient. We pay the efficiency that, we pay for that efficiency by being incomplete. Okay?
So you mean there's a simple, inefficient, but complete algorithm?
Yes, that will work. Again, complete means refutation complete, so that will work when the problem is unsatisfiable. But that algorithm will not work when the problem is satisfied.
Oh.
Okay? Now, I have to say,
So if you run them in parallel.
yes, we don't actually have, if you run them in parallel under the right assumptions, so I would have to give more details here. You do get a decision procedure, but again, the right assumption identify fragment that we do know is decidable. Okay, so in fact, our decision procedure might also loop from certain in certain satisfiable cases. Okay, if I have time, I'll tell you a bit more about this later. The point is, we have a looping situation here. Can we address it? I will just flash this. I'm not going to go into it. You can prove that an equation like this, where S and T are arbitrary string terms, and again, X is a variable, is equivalent to this problem. So essentially what we do is, given this, we introduce this sort of these constraints here, where Y and Z are fresh variables. And notice that we have some equalities here that essentially have to do with the fact that there's some sort of reverse thing going on here. But the important thing I want to stress is we also introduce a regular membership constraint, which is symbolic. These two are variables. Okay, that's why we need to deal with symbolic membership constraints, even if the original problem didn't have them. Okay. Again, I won't focus on membership constraints. If you're interested in this, I'll be happy to give another talk at another time. Okay. But again, we have a way to address these sort of simple loops. Now, suppose we have applied this normalization, these normalization rules, which again, I'm hand-waving about right now. I will show you the rule later, time permitting. Once we have normalized, then we have a bunch of equivalence classes between string terms where every equivalence class has a normal form. Let's partition these equivalence classes. How do we partition? We put them into buckets, as I said, where equivalence classes that we know are different go into different buckets, for sure. Okay? So for instance, suppose I know that the length of T1 and the length of T2 are different. Definitely T1 and T2 belong to different classes, 1. And 2, I know that I can't merge those equivalence classes, right? Because you're supposed to have different lengths as string terms. So T1, T2, and T3 in this case go into different buckets. What about, say, T1 and T4? Suppose I do know that T1 and T4, well, T1 and T4 are in different equivalence classes, okay? But I know, say, that their length is the same. Then they go into the same bucket. I will assume that stuff that I can put in the same bucket can have, each equivalence class can have a different string value of the same length. Why? Because if it can't, it means that I have to merge the two classes. And so, in fact, I have one class, not two. Okay? So this is the partitioning mechanism. why is this helpful? Because basically it allows you now to compute an actual model of the problem, where by model mean a assignment of string variables to string constants that satisfies the constraints. Okay. In SMT,
Not equal to T2, not
sorry?
equal to T3. Is that at the bottom you have that thing?
Yeah, these are the lengths. The length of
Yes.
T1 is different from
Yeah,
T2.
so is that two inequalities or
Yeah,
is
that's
it
a
three?
good question. I really meant the 3, but
The
I
3, okay.
wrote it sloppily that way.
So if you only had 2, then it would be a bit harder to...
If I only had 2, I would need to guess, again, where to put them. I mean, this is a standard, at this point now, this is a standard constraint satisfaction problem, right? So, I have these many buckets, I have these many terms, I have to put them in there, right? How do I do this?
Okay,
So
the partition-
guesses are involved here again.
And that involves backtracking too.
Sorry?
That involves backtracking.
Obviously, every guess might involve backtracking. Yes. This is essentially a CSP problem analogous to a coloring problem. Okay. So again, standard techniques apply there too, and they are implemented in our solver. The interesting aspect to consider here is that when you put stuff in the same bucket, you're saying they all have the same lengths, but they have different values. But now you got to be careful. Like, do I have enough values of that length in the string domain, right? For instance, I can't have, if I have 2 characters, I only have 2 different strings of size 1, right? If I put 3 things in there, I have a problem. So the next step is to generate cardinality constraints that capture this. So we add cardinality constraints that are meant to make sure that the assignments that we make into buckets respect cardinality restrictions on this domain. Okay. Once we do that, and everything checks in the sense that we go through this whole process again with nothing being produced, then we have saturated. We have shown that at the end of this process, we have really computed a satisfying assignment for the original problem. just to stress, sorry?
Sigma is known and fixed.
Yes, maybe I should have said this from the beginning. Our alphabet is finite. Okay, it's known and finite. Now, of course, the algorithm is parameterized by the alphabet. The actual implementation isn't. We're using 256 characters, the ASCII characters, and so on, but you can easily change it that way. But it is important that it is finite. If the alphabet is allowed to be infinite, then you don't need the cardinality check, right? Because a bucket can have as many things you want, because you can always get a new character to make it. Okay? So at this point, we're done. I mean, hopefully I've given you the general idea about this algorithm. How do we actually do this? As I said, we do it by using these algebraic rules. You can understand the process, or you can describe the process theoretically as a tableau calculus. This is how we actually do it. And then you can prove properties about this calculus. They are satisfied by any proof procedure that has, that satisfies suitable restrictions. Since the implementation is effectively an implementation of a proof procedure, then the properties that we discuss about this calculus are inherited by our implementation, modulo bugs, of course. And so what can we show? That if in this calculus, which being a tableau calculus produces a derivation tree, if I close the tree, that is, at every branch I get an inconsistency, then that tree indeed tells me that the problem is unsatisfiable. Okay, so I have soundness, refutation soundness. If one of the branches saturates, as I mentioned before, we actually find a solution for the original problem. Okay, so the problem is satisfied. We have what we could call solution soundness. And that's it. We don't have termination. We don't have refutation completeness in the general case. However, those experimental results that I'll show you in a bit tell us that, show us that in many, many cases we actually produce an answer, a set or set. All right. if you're interested, I'm just going to flash the rules here. The rules of the calculus that formalizes this process. There is the calculus was published in the CAV paper from last year, and we're submitting just this week a journal version of it, which has a lot more details. So if you're interested in this, just let me know. I'll be happy to send you the journal version. The calculus works on a bunch of components. We call it configurations that stores the various constraints. So there is an S component that has just the string constraints. There's an A component that has only the arithmetic constraints, plus other things. For instance, we build a normalizing function that uses something that we call a flat form and so on. So we have several components, and each of these evolves, is modified by the rules. Okay? So we have some standard, trivial rules, for instance, propagations. If the string component entails that the length of x and y are the same, tell the arithmetic solver. Okay? And how do we discover this entailment? By just using congruence closure. Okay? So we have simple ways to discover these entailments. If the arithmetic constraints entail the length of x is equal to the length of y, tell the string constraint. How do we know this? Well, we're using an arithmetic solver. Okay? What other things do we know? I mean, suppose we know that these two terms are supposed to be the same in the congruence closure of S. That is, S entails they're supposed to be the same, where x is a variable and t is not a variable. Well, x is a variable and t is an arbitrary term. So then tell the arithmetic solver that these two terms have the same length. Okay? So this is the sort of stuff that goes on. I told you about splitting every variable, deciding what length it is. So if x is a variable, then guess that it is the empty string or it has a length greater than 0. Okay. This is a rule that breaks the loops. Well, we do have another unsatisfiable rules. If the arithmetic solver discovers an inconsistency, definitely we stop. Okay. We have additional rules I haven't mentioned before. And these are sort of technical. Well, the conflict rule in the string solver is the obvious one, right? If two terms are equated and inequated at the same time, you find a conflict. But we have the subtle split rule that says, well, if you don't know whether two variables should be the same or not, then guess. Okay? So again, this shows you that we're dealing with an NP-hard problem, so we do need to make guesses. We also have a reset rule that says every time you deduce a new equations between terms, all the data structures that you computed so far, recompute again. What are these data structures? Are the ones that tell us what the normal forms of stuff is, right? If you have a new equation, the normal forms are going to change. Let me just tell you quickly about the normalization process. The slicing process that I mentioned before the slicing process proper is done by other rules, but the normalization process, when you're done slices, is done this way. Every term is associated to a flat form, which is, again, just a sequence of atomic terms, constants or strings. Okay? Now, excuse me. At the same time, every equivalence class of terms is associated with a normal form. Okay? Normal form has the same form as a flat form. The difference between the two is that the normal form is final. Unless you add more equations, I know that this term isn't supposed to look like this, whereas a flat form is an intermediate representation. And how do I go from a flat form to a normal form? Well, I look at the equivalence class as a class of a term t. If all the terms in the equivalence class have the same flat form, then we're good. We can make it, promote that flat form to the normal form and associate it to the whole equivalence class. Okay? How do we compute the flat form to start with? Well, bottom up in a sense. Suppose t is this shape. By con here, I mean the concatenation of t1 to tn. And I have computed the normal form of t1 all the way to tn. Then the flat form of t is just the sequence of all these normal forms. Well, possibly normalized a little further, but let me just sweep that under the rug. Okay? So this is the idea essentially. These rules do the slicing, And notice that some slicing is actually involves no guesses. If S and T have these flat forms, that is, have the same prefix W, okay, and you know that U, an atomic term U, and an atomic term T have the same length, then you must equate them. Okay? This is how you derive new equalities. In a situation where you don't know whether U and V have to have the same length, okay, then you guess that one. Sorry. When you know that they don't have the same length, then you guess that one is longer than the other. And you continue that way. Finally, these are the rules for doing the buckets. Let me skip those. And I mentioned the theoretical results, refutation soundness and solution soundness. We also have solution completeness. At least a version of our calculus or our procedure is solution complete in the sense that it's guaranteed to produce a solution if the problem is satisfiable. And this guarantee is achieved by finite model finding techniques. So essentially, we go back to bounding now the length of the strings, and we try for increasing bounds of the length. The bounding is done in a fair way so that, again, we explore all possibilities fairly. If there is a solution, obviously, it involves assigning variables to finite strings, so there is a global upper bound at that point. Notice, however, that the solution complete version is slower than the regular one because it's a depth, iterative deepening kind of process versus a depth first kind of process that we follow in the general case. So this is solution completeness as a cost. The approach is refutationally incomplete, as I said. However, we have identified a fragment which it so happens is equivalent to a fragment identified by others and discussed in another CAP paper that we call acyclic problems, where our approach is also terminating and so refutation complete. Okay? So in essence, acyclic problems are problems where you don't have repeated variables, or if you have repeated variables in a problem, they are controlled. There's a controlled form in which you have repetitions.
Let's return to the previous slide a second. So this is all about performance, really, because I think there's a solution complete and refutation but refutationally incomplete algorithm, which is just enumerate all the possible models starting from the smallest
Obviously,
ones.
there is a trivial
it's a
case.
Slow, but
yes.
As
I said, we are interested in efficient solutions, right?
And
so this one is definitely more efficient than the naive algorithm. That's for sure. but it's slower than the incomplete one. That is, experimentally, right? The majority of problems that we consider are solved by the fast incomplete ones, of satisfiable problems. Okay, so the incomplete, the solution complete one gives you this guarantee, which is often not really needed because the other one is fast enough. It is good enough. The fast one is good enough.
If the worst case is very bad, I guess your hope is that if a typical case is, you're going to be pretty quick.
Yes.
In practice.
Our implementation is done in a solver that actually can be run in a portfolio version, where you run different configurations at the same time. So you can always run the solution incomplete one and the solution complete one in parallel, and knowing that you will get the answer and fast enough also.
Is there a sort of standard corpus of these string-like problems that you're able to?
I'm sorry.
Is there a standard corpus of these string-like problems, rather like the SAT-solving competition and the? Is there one for these strings that you could?
This is all new. I mean, it's really out of the fresh out of the oven. So we don't have a competition yet. However, I happen to be also the one of the main coordinators of the SMT-lib initiative, who also runs SMT-Comp, and we are devising a standard theory for this. So hopefully next year we will also have a competition.
Next year you'll win the competition.
Well, we win it now. We would win it now. If we had a competition now, we would win it. However, we also need new problems. Okay. So the hope is that by since now we have solvers, we're going to get more problems from users. And in fact, there is a huge need right now. We have users that get our solver as soon as we check in, the new version on GitHub. They'll download it, users, and give us, feedback and so on. So there's a pent-up demand for string solvers in the community. By community, I mean verification or security community.
I mean, bit blasting is really bad.
Sorry?
Bit blasting strings is really bad.
Well, not necessarily. I mean, if the problem is small enough, and no, but you can do a lot of stuff. So there is this Hempy solver, the one that's being used until now. It's very useful. It's still very useful. It just doesn't scale, right? So that's why we're working with these different approaches. And by the way, we're not the only ones anymore. I mean, there are a couple of other, well, 3 in fact, I know of, concurrent approaches that are solving the same problem. All right, so our experimental results. As I said, we've implemented this in our CVC for SMT solver, and then compared the solver against a previous solver called Kaluza that used a series of heuristics, but is not technically an SMT solver. But it was the best that there was, for a long time. Then this, competing solver, so to speak, called Z3STR, built by some colleagues at Purdue and Waterloo, in fact, that actually realizes, it implements a string solver on top of Z3. You guys know about Z3? Okay. So technically, it's not Z3. It's a modification of Z3. It's called Z3STR. In fact, there's a new one that don't have in the slides called S3, which itself is built on Z3STR. Okay. So the top solver. Well, sorry. Finally, there's another one called Norm, but this is really new. We don't have any experimental evaluation with Norm. Norm will be hopefully presented at CAV. And let me just quickly give you the results. We consider almost 50,000 benchmarks generated by a web security application. And, well, it turns out Kaluza is not what we would consider a good application right now in terms of solving. It has all sorts of problems. It's both unsound, incomplete, doesn't produce solutions. So, we've really improved tremendously with respect to the state of the art at that point. The comparison with Z3 is more apt. I mean, G3STR is a more serious string solver, so to speak, except that for some reason is not able to compute complete solutions. That is, often it will, well, in a number of cases, will return partial solutions. Not all variables are assigned a value. We don't know yet this. We're investigating with the developers. But you see the numbers, in terms of performance. And I guess it's easy to see that, well, first of all, we have no unknown answers. We do have timeouts. No known errors. We have checked the solutions against, the solvers against each other and so on. Z3, SCR, and CDC4 produce no errors. Kaluza produces a lot. In terms of raw performance, this picture gives you a sense of how it goes. This is cumulative runtime. Okay, so this is CDC3, and of course, the y-axis is on a logarithmic scale. So the majority of the problems here are trivial for CDC3. Then it gets hard quickly, in a sense. But for this version of Z3 that Z3STR that we tried here, it gets hard a lot sooner. Although right now they have a latest version that flattens this a little bit. Kaluza is hopeless. Okay. And I'm done. Well, let me tell you about additional work. We've been working, as I mentioned, also regular languages, and we identified a fragment where we actually have a decision procedure. This seems to be a no result. Okay, not published yet. We're interested in, we're looking at more fragments where we have refutation completeness. We are working on optimizing performance because we have real customers that want this thing and so on. And in particular, they want these other string manipulating functions like index, substring, and so on. And a lot of this work can, in fact, be generalized to a parametric theory of sequences, where you don't actually have strings of characters, but you have sequences of anything. There, again, you need to ask yourself whether this anything is a finite set or an infinite one. Okay? And I would like to say, I'll take your questions now, but I got a lot, so I'll take other questions now. Thank you very much.
Cesare is visiting PPC until the end of the week, so there's plenty of time for interaction, follow-up questions if you desire. So. Okay, so all the questions during lunch. Thank you.